Okay, well, more may join, but I will go ahead and kick off this talk. Thank you so much. It's my honor to introduce Dr. Flora Salim, who is able to join us today in large part because she is traveling through the US. She is actually coming to us from University of New South Wales in Sydney, where she is the Cisco Chair of Digital Transport. Those of you who, like me, work in machine learning and ubiquitous computing, I'm sure know of her work. She's been very active in ubiquitous computing, behavior modeling, trustworthy AI, and machine learning for multimodal sensor data. And she's also very active in all of the work that's going on in various publications in this area. She's editor or associate editor-in-chief for publications including ACM MWIT, IEEE Pervasive Computing, ACM Transactions on Spatial Algorithms and Systems, and she's a member of the Australian Research Council College of Experts. So it's a rare and terrific honor to get to hear about her work. So I will turn it over to you, Dr. Salim.
Thank you so much. It's really, truly an honor and privilege to be here and to get invited to give you a seminar. So the honor is really mine. So thank you again, Diane and Maureen. Let me just share my screen. Okay. Right. So just confirming that everyone can see my screen.
Yes,
Great.
that's fine.
Let me just move this Zoom panel somewhere. I'm normally used to extended screen setup, but now that I'm using my MacBook, everything is crammed on just one.
While you're figuring that out, I'll just remind everybody that
okay.
if you want to put questions in chat, that's great. Otherwise, we'll field questions at the end.
Yeah, so I've got my chat also on the side. So if there's anything you'd like to ask, feel free to fire your questions. All right, so the talk today will be a combination of overview of what we do in our research, but also some of the problems we are interested in general, but also some of the techniques that we've proposed in the last few years. So today I'll talk about robust behavior learning from multimodal time series with self-supervision. So I'll also expand on what self-supervised learning is. I wonder how many of you here are familiar with self-supervised learning. So I just want to know how much detail I have to go through in terms of self-supervised learning. Maybe
you probably have a
raised?
mixed audience. Maybe half of the people are.
Okay, great. Then I'll do a quick overview as well. Now, so you can see on the top right corner is a picture of my lab. And I've just moved to UNSW just over a year ago. So I have still a couple of students at my former university, RMIT University, but the new group is we'll be building up a new group. So we've got a couple of new PhD students and I've got 2 postdocs that move with me from RMIT. We also have a couple of visitors. So if you see, there's a lady there. She's actually a Fulbright professor or fellow visiting from the US, and just actually returning this week back home. So I always welcome visitors. If you like to, think about visiting us, do let me know. So these are the different areas we're looking at, mentioned by Diane, but let me just go through. So I'm very much interested in multi-scale behavior intelligence coming from sensors that are either from on body, so wearables, or sensors that are attached to our critical infrastructures in cities, on the road, in buildings, and looking at multi-scale behavior modeling. And the reason why is because there's a lot of IoT devices in many domains, and if you think about it, typical pipeline for behavior recognition in, maybe 20 years ago, you have to think about who you want to monitor. You have to plan how to actually, which sensor you're going to use, how do you deploy them? Is it going to be camera based? Is it going to be wearable based? Is it be a combination of both? Is it wireless sensing? For example, do people have to carry anything? Do people have to be compliant? So there's a data collection protocol. You have to be thinking about how do you label it, right? Because typical machine learning process, typically supervised, fully supervised, which means, and we all know garbage in, garbage out, and we want to make sure that the data that you have is has a really nice, clean, labeled data, and you train them, and you have a training test validation set. You even have, even before that, you have to decide on the features. So only you get to do the fun part, which is the modeling, right? So you can see so much different steps before you even get to there. So if you look at this, there are a couple of major bottlenecks. So even if you think, oh, we want to do behavior modeling in the wild, you still need to have some sort of way of, okay, let's do it in the wild, rather than having people to keep doing self-reports. That means you need to have camera-based system to at least know what's going on in order to validate what you do, or you have an observer in the room. Again, all of these are a lot of bottlenecks. And these things are the typical approach that actually required for fully supervised machine learning models. So we started moving away from that. Just giving a couple of examples further down. So the reason why, because it's this exercise, the whole exercise here, to do it perfectly is very expensive. Data collection exercise is very expensive, and you typically you don't get huge number. You can't really get a huge number of participants, and even if you can try get really nice data sets, they could be biased to a certain population. Requires domain expertise, and yeah. And these are the type of inference tasks that we've been looking at in the past 10 years. So from your basic physical activity recognition, using sensors on the phone, wearables, do we know if someone is walking, running, sitting down, or sleep activity? We've done sleep activity as well, and sleep apnea, the type of category sleep apnea, emotion, stress, and all those things. We've done abuse prediction as well. I'll show you a couple of different examples. So we know the combination of this, and I'm sure people in this Zoom room, a lot of you have been doing digital phenotyping, which is looking at the biomarkers that might come from your wearable sensors or any other sensors, and combination with self-reports, and how do you actually profile your subjects, your patients, your users. And there are a couple of things that we've done in this area of digital phenotyping. So in terms of behavior, engagement, emotion, mental health, concentration, stress, and a couple others. Now, I just want to briefly show you this one particular data set, just to even make my point further, but I'm also keen for you to take a look at this data set, and possibly could be useful for your own study. So this was collected at a high school. So the project's funded by through an ARC, and also a company called Oricon, who actually had who's actually interestingly an engineering company assigned to do new high school building, and they wanted to be they want a building to be conducive to the teaching environment, so people can actually be improving their learning conditions. So how do we build some kind of sensory smart environment to be able to know whether students are engaged in their learning? So we deploy a lot of different sensors, so including all these different sensors, indoor weather station, and even we sensorize all the windows and the doors, because it's people can turn on and off the aircon or open the window, and they're using these E4 sensors with one variable, so it has a accelerometer skin temperature, EDA, and you can also compute the HRV from the census. And we have the survey after every class. So we collected all of this data and just going through this really quickly. We had about 30 participants, including teachers. And we adopted some gold standard thermal comfort survey, and also gold standard student engagement questionnaires and affect questionnaires into something that can be done in just 2 minutes after every class. So we collected all of these. And the students move around in different classrooms, so not just one classroom. Remember, from the engineering company point of view, they're very interested to see from the classroom, the heat, temperature, and all that, and solar radiation. How is it affecting, the performance of the class? And we actually look at the individual performance of the students as well. So this was actually, that's the Nature Scientific Data paper. And this is the part where we have done IMWOOD paper, combination of these data sets. This is the bit where we do just the typical machine learning pipeline. The data is really noisy. We collect the data. So my student had to go every day and got the data from this wristband every day, because it's actually it's not wireless, so she need to actually upload it and then put it back and recharge the battery and put it get the student to wear them again, going through all this process, including segmentation. So I'll show you about the segmentation algorithm further down the talk, which is very useful for any data cleaning purpose. Because some students may take off the wristband, may put it on, or a lot of different things. And we extracted a lot of different features from these census, and based on that, we also then compute what is the emotional engagement, cognitive engagement, behavior engagement, and overall engagement across different classes. So language, math, science, PE, politics, health, chapel. So this is a Christian college. So year 10 students, about 15, 16 years old. So you imagine, even before data collection, we had to brief the parents. So we had to get their consent. So this was actually really a lot of work. And we actually found a lot of interesting findings as well. For example, the cognitive engagement actually is actually really low if, the students prefer cooler thermal preference, which means the room is really hot. And we also found with, for example, sensor data, when it's not here, you can see the details in the IMWOOD paper. But for example, when CO2 really high, the cognitive engagement dropped, especially, and it affects when they have to do STEM subjects like science or math. So that actually really help us to understand that, you can help teachers to how to schedule the class appropriately, whether doing it in the morning or afternoon, how to actually monitor the condition in classroom to improve the engagement. So I'm glad that paper got a distinguished paper award from IMWOOD. And there's a lot we haven't done with this data set, but we've just put it out there. For example, we haven't even done the engagement between teacher and student. We've got a teacher data set. We just haven't done anything about it. We just haven't had time. So it's all open. Feel free to use it. So we've done a lot of these things. As I say, it's a lot of work. Data collection is a lot of work. We've done with workers as well. So we've done it in another engineering company. It's an open plan workspace. And can we predict whether they can concentrate or how stressful they are as they move around? So one of the majority of the signals that we look at is always mobility signals or movement signals, and in combination with EDA and all of those things. And one of the recent work we did as well was, this is completed, a collaboration with Microsoft. So Microsoft Cortana Intelligence Institute, we were funded by Microsoft Research. that look at combination of cyber-physical behavior, we call it. We propose that. So physical movement and behavioral physical behavior movement, the physiology from the physiological signals, and online behavior such as app usage on desktop and then also mobile, to know what they're looking at and what they're doing in terms of, and can we predict the tasks they are on, and then can we recommend tasks that they might be interested or need to do in the future. So these are a couple of things that we've done. So there are a couple of papers in relation to that as well. So I'm returning to this slide because, as you can see, we've done a lot of those things, and I'm sure you have done these things as well. And it's a lot of work. So how do we then move to the scenario where we want to learn from open world with data in the wild? So data can come from anywhere. It can be, it might have been collected by a company, and they say, we've got this data, could you tell us, important insights from it? Or, it might be something that, a project, but you just have no budget to collect data, whatever. But, let's look at data sets that are available. And I think another problem is data coming from the wild. It's noisy, data distribution can shift, and sometimes what you observe may not be a representation of the true behavior, and behavior shift as well. I mean, as you know, we had, COVID pandemic, and then you had lockdown, and then people behavior shifted because of COVID. Now, you and I, we are zooming into this meeting, right? So we don't go to work every day. So how do we then build not just multi-scale behavior intelligence, but how do we build robust? So, and I've mentioned already that a typical machine learning algorithms require high volume of training data. But the problem is annotation doesn't come cheaply in our field, in ubiquitous computing. Fei Li has amazingly given us with the gift of ImageNet, right? But it's much easier to annotate a cat or a kangaroo rather than annotating this, right? Please, let's get a crowdsourcing and let's annotate what's going on here. Hey, it's very hard to find even the expert to be able to annotate this, right? Now, if you just quick question, which of the two ECG sensors sample that shows someone with cardiac arrhythmia? Top or bottom? What do you reckon? Anyone in the chat? Okay. All right. Very good. It is, normally I get a mixed response, but let me show you. So you're correct. Only after you've done a wavelet transformation, you can see clearly the one that has cardiac arrhythmia is the top one, right? But with just your pure eyes, without any feature extraction, you won't be able to see it clearly unless you're an expert, right? So it looks like people in their room responding, and they're obviously the experts, right? They can tell it right away, even with the feature engineering. Now, so time series, spatial temporal data have all these issues, not just unlabeled, but they're irregular, they have multiple resolution, they always have missing values, and there can be different sources. So so how do we develop machine learning models with less labels, less samples, so you don't even have much examples to work with, especially when behavior change, and less resources. So a couple of things, a couple of tricks we've worked with, but what I'd like to focus on today is the self-supervised learning bit. So we started doing self-supervised learning since 4 years ago, because we can see that problem. And basically, what is the framework of self-supervised learning? You have original data with no labels, and you can do pre-processing of these data. For example, using change point detection, at least a bit of amount of cleaning is done, through some pre-processing. And then you can do pseudo label generation. So this is a typical framework, right? Pseudo label generation, you can do it explicitly or implicitly. You can use augmentation, for example. And then you can pre-train this model using these pseudo labels you've generated either through augmentation or pretext tasks, and come up with a latent-based representation. And then once you have this pre-trained model, then you can have small label data for downstream tasks. So this is very much also the paradigm behind ChatGPT, right? So GPT, generative pre-trained transformer, is a pre-trained model, largely pre-trained using the transformer architecture, and it actually has a lot of this part, which is the pseudo label generation. Now, so I started by saying that you can do data cleaning, for example, using change point detection. The problem with no label, sometimes you don't even know the boundary of these data. So if the data coming from sensors in the wild, people use the wearable data, and you don't know, you weren't part of the data collection. How do you know what are the even n number of classes that are available out there? So we've done things like, for example, change point detection for basically looking at boundary of classes. And for the extreme cases, you can consider it as anomaly detection. So one of the earlier work we did was information gain based. You can actually, how do you define the time series to most homogeneous segments that give you the most information? And you can take a look at the paper, and we test it on different data sets. And we often use just these algorithm of our that we use ourselves, IGTS, just for pre-processing, and then we do further things on it, just to be able to look at how many potential number of classes there are, or clusters, or classes to basically number of classes. Now, so you could see that actually IGTS is not just very accurate, but also very fast. That's the time taken to segment it. Now, but there's a couple of weaknesses with IGTS. It does not work in all cases of changes. And we got the IGTS in MATLAB and Python, so feel free to use them. A lot of people have used them. Even my own undergrad students have used them. And we found further that certain change point detection algorithm do not work with shape-based changes. So it works very well for statistical changes, but it does not work for shape-based changes. So in here, there's a shape change. You may not notice it because statistically they look very similar, but you can see a flip of the shape. So it goes from here to there, for example, right? So and this happens for example, hand gestures, which are normally, for example, eye movement. If you do eye tracking, you do eye movement change. It's, if you do, for example, looking at statistical pattern, very similar, it's just the shape change. So we combine the entropy base with shape-based changes. We call it espresso. Again, the details are in the paper. The code is publicly available. And we can see that espresso is even more effective than IGTS. So we combine, actually espresso is a combination of IGTS and FLOSS. FLOSS came out of Eamon Keogh's lab. So we got this idea after I visited Eamon, and he talked about FLOSS. So and we actually did a comparison that, in fact, in some data sets, Eamon's ones works well in the shape-based ones, but when we combine the two, it's even better. And I just want to give you a couple of examples. There was one data set we use. This was a live logging data set collected by a guy called Cathal Gurin from Dublin, DCU in Dublin. He ran a challenge on live logging challenge of his own life. And it's like 5-6 years of data of him wearing this sense cam. and it has accelerometer and also the camera. So and we just did we want to see if his behavior change or there's behavior deviation routine changes. And again, we use espresso, for example, so if you can see before, the espresso could be used on physical activity recognition, but this was actually just daily behavior, daily routine behavior. And we found shift in some of his behavior, and we actually sent him a lot of some of these data time points. We said, we found a shift on this day at this time. Can you tell us, and there's no annotation in the data set, so there's only camera, right? We could try to explain, right? Okay, typically this person goes to work, but it's not. The camera shows that we didn't use the camera data. But then he actually then wrote back, said, yep, this is what happened. So somehow he also wrote a diary aside from it, but that diary is not part of the data set. But it was interesting that he could verify them. So we found this to be quite useful, even for emotion changes, for example. We can detect emotion change much earlier than when it's actually marked as emotion change in the data set. Now, the problem is with these two, there's further weakness in these two algorithms. When the data is really huge, it's and again, these are unsupervised method. Really great for pre-processing, but they are not a model, right? Think about them as unsupervised clustering-based kind of algorithm. And how do we build a model with self-supervised learning techniques? Remember that if we want to build a good representation, they need to be, for sensor data, they need to be compact, representative, and they need to be robust. And we want them to be reusable for downstream tasks. So just going back to the paradigm self-supervised and supervised. So if you use supervised learning, you've got data sets with labels, for example, X and Y, and model would say, oh, yeah, that's a Y. And so you train these and you come up with a supervised model. So in here, you've got no label. So how do you then train a model without a label? So there's this part where typically is used, which is the pseudo label generation for a classification task. And for more details, take a look at this review paper. We've got I think quite a comprehensive one. We keep updating it. We'll re-upload the archive. The review takes so long, it's still under review at the moment. So if this is just the most basic there are a lot of different variations discussed in the paper. So so if you look at this, so this is the more expanded version. So from the unlabeled data, you can do the pseudo label generation based on different transformation, augmentation, and all that. And then you build a representation learning encoder based on certain objective. So you need to basically minimize the loss based on that objective function and all that. And you've got that pre-trained model that it can be reused multiple times for different type of downstream tasks. So the downstream tasks, you then have the label data, and you extract that representation from here, and then you have your classifier. So the main idea is, this came out of computer vision. So a model will be able to detect that these cat images have very similar representation, and those parrots will have similar ones. So although they don't use label, it's using its own data as a labels. For example, with the cat images, is going to do a lot of different transformation. You might be doing some kind of rotation. You might be doing certain pixel-based transformation, and then you basically you're saying this is label X, and all of these are of a label X because they come from the same image. So this way is a pseudo label generation coming from its own data, so-called self-supervised. So at the end of the day, you basically have a representation that's basically saying all of these are of label X, although I don't know it's a cat. Okay, so that's how it actually works. And it's the same thing, we can do that for sensor data. Now, the problem with these, though, how do we build a representation space for sensor data that can, basically do this? So in contrastive learning paradigm, for example, there's different approaches in contrastive learning. How do you maximize similarity between these positive pairs and minimize similarity between negative pairs? So I mentioned before, for example, all cat images, it's from the same image. It doesn't know this is the same cat and that's also another cat, but it's basically from the same image. We do all kind of transformation and representation that are from the same image that's transformed different ways. They are called positive pairs and the rest are negative pairs. And then you learn it that way. That's basically how contrastive learning works. Now, one of the first earlier work we did is then change point detection. That's why I started with change point detection, so you know what it means, right? So change point detection, how do we do contrastive learning for change point detection? So that basically means if we deploy this model, you'll be able to detect there's a change point, and or maybe it could be a transition to an existing class that we know, or it could be a new class emerging that we've never seen before. So that's basically downstream task or anomaly detection. So we don't care about the downstream task. What we want to know is the pre-presentation is to be able to do change point. Now, how do we come up with this idea of positive and negative pairs for time series in change point detection? So back then, when we had this paper, we were the first in the world that came up with this self-supervised learning paradigm for change point. And we found out a few months later, there was someone who plagiarized the paper, came up with exactly the same, but submitted somewhere else. Anyway, and it's still there. It's still out there. You can see two versions of the paper. So how do we come up with representative feature factors from these semantic segments to enable change point detection? The backbone is TCN. You can use any other backbone if you like, but basically we use TCN because one of the state-of-the-art back then for temporal convolution for time series. But the whole idea is we think we could look at, we can define what positive pairs as those that are actually closer together and those further apart as negative pairs. So these are very naive assumption, but it worked. So basically, how do we, if you have samples coming in and the closest one in the future, the next step, time step, they should be quite similar. So we call them positive pairs. And how do we then minimize agreement between those further apart negative pairs? And I'll skip this part. So so our hypothesis is, so if there's a change point within the embeddings, then the distribution will be quite different. So how do we then compute that also? Differences of those. So we use cosine similarity between these latent embeddings between of history and future interval. And we look at, we just took some samples of representation that were learned, positive and negative pairs. And we, from the samples that we did, we found that, these are the positive pairs and these are the learner representation, which look very similar. These are the ones without change point, and with the change point, they look different. So that means, okay, the representation learning works. And if you could see our result here, KLCPD, actually, our work even outperformed our previous one, which is Espresso. It's also beat this paper, KLCPD. So this is the improvement over KLCPD. So TSCP2 outperformed KLCPD. KLCPD was published in Europe's that year. So this was published in WWW. During the same year, we also look at COF classification without labeled data. So back in early 2020, as we know, we had a pandemic. No one could forget that time. And a lot of people, a lot of academics around the world, they develop app to collect cough sounds. You remember MIT, Cambridge, IS Bangalore, a couple of other, I think Oxford did the same. So there are many of them, but there were papers on using cough audio or respiratory sound, so people coughing and asking whether this is COVID or not. These data are collected, but the people did not report back after a PCR test or rat test that yes, I was positive, I was negative. So maybe only 9% of those data sets were labeled in any of those repositories. And the models that were used only used those 9% to 10% data sets. They didn't use the rest because the rest considered either noisy or you can't use them because they're not labeled. So we use this contrastive pre-training with the idea of let's just use all of these unlabeled respiratory sounds. Let's build a pre-trained model. So can we then use this, and then only downstream tasks we use the label data. And so that's what we did. You could see the details more in our KDD paper. So from the process audio, we did random masking, and we use a transformer architecture, and we compute the contrastive loss of basically the transformation that we did was basically using random masking of the same audio. That's how we did the contrastive of positive negative pair. And downstream, then we use the label data set because it's actually adapting. We also adapt the same masking generator, and then it knows, okay, this representation is related to COVID. There may be some parts that are related to something else, maybe a TB or COPD, but we don't know. We don't have that label data. If somebody else have these data sets in this room, happy to test, do other downstream classification. But in that paper, we only did COVID. So we did different settings, ablation of different settings. VGGH, a lot of people use them. Just VGGH fully supervised with only the labeled data. And then we use GRU transformer, and then we use transformer base with self-supervised paradigm. So we thought, hey, normally if it's if you use fully supervised, you should be the most accurate, but our self-supervised ones actually is more accurate. And I think this is the power of large-scale data. And this is why large language models these days are so powerful, because it's trained on the internet data, right? Because that's a paradigm. Now, we've seen time series, we've seen audio. What about multimodal? Now, the problem with multimodality for contrastive, a lot of contrastive learning objectives are only applicable for pairs. So how do you do it with multiple modality? So even the most recent paper from Meta, highly promoted by Jan LeCun himself, they also train one on, for example, accelerometer and audio, for example, I can't remember. But there are a couple of these data sets they try on, they call it they're the first in multimodality. But if you look closely at their evaluation, they've only done it on maximum 2 modality. None of them can do more than 2. We were the first that did it with more than 2 modalities. This is an Amwood paper last year. So if you have single sample, you have multiple modalities, sensors coming from accelerometer, gyroscope, and maybe these sensors are not just on the body, it could be something on the phone and something else. So we came up with this COCOA objective function. The details are in the paper. And basically what we call positive pairs in here are sequences across all senses, and the rest are same sensors, but they are not temporally aligned. We call them as negative pairs. And basically also we can look at positive pairs selected from different sources, and this results harder positives. So we basically do computation on this objective function across whether they're positive and negative pairs and whether they're harder positive, harder negatives. And we applied this on different data sets. So the human activity, opportunity data set, sleep stage detection, and emotion recognition. So we use the same encoder for the 10 baselines. And there's different setting whether we freeze up the pre-trained encoder or not. So we outperform the fully supervised baseline, so fully supervised here, and also COCO has less computation in comparison to CMC. So CMC was the closest work before COCO, but CMC could only do up to 2 modality, not more. And also data efficiency is how many percent of labels are needed to do the downstream. So that's in terms of fine-tuning stage. So that's the best supervised outcome, and that's our work. So please take a look at the paper for more details. So we were the first to apply that contrastive learning for multiple senses of different modalities. It's label efficient, and it also performs well with smaller batch sizes. About 3 years ago, we also have started doing SSL for on the edge. So can you build pre-train? We didn't do pre-training here. We just built basically a self-supervised, we call it scalegram contrastive network. So basically from the same EEG signal, for example, we do augmentation with, for example, transformation of waveflow transform. And so with the same raw signal, we use contrastive signal, so we can then have a pre-trained model on the edge. And then you can federate the weight of the model to build a more group-based work. So for example, this was evaluated in sleep stage scoring, activity, stress, and the visualization of using TSNE of the learner representation without labels. You could see they're separated quite nicely. And even with smaller number of instances per class, it outperformed the fully supervised model. So the main difference of this paper and previous one is we had I don't have the details here, but we had this bit where you have the on-device learning and you have the aggregation, the federated bit. So federated bit is very simplistic. We only use averaging, just federated averaging, just like proposed by Google. So, but it actually worked very nicely. But what we show here is basically you can also do SSL on device. So we were the first who did that for in our field for census. Please take a look at this survey to learn more about SSL for multimodal time series, because we have a lot of different explanation of different types. And if you look at the existing methods, most of them came out of computer vision domain. So they're not suitable necessary for our sensor time series domain. So a lot of them have to be adapted. One of the most recent work also, I don't know how much time we have. How much minutes I have left, Diane?
Maybe another 5-10 minutes.
Okay. So this is one of the most recent work where the question we have is, what if the pre-trained model has to be updated? So let's say if we have pre-trained model, right? And we have different settings here, whether if there's new data coming in, right? Whether if we update the pre-trained model, how does it work? So it's basically active representation learning with incremental data. The data maybe come every week, right? And we tested it on different scenarios. You can take a look at the details of the paper. So in some situations, it works nicely, some have not. So if you look at this, this was just still a short paper, still very much an ongoing work. we still haven't fully answered the question, in what cases we need to update the pre-trained model. So that's basically the question. And we also try on adapting it to different, for example, we train it in UCI data set, for example, hard data set. Can we use it for sleep, right? So the downstream task is something else. So this is still an ongoing work. And so you've seen a lot of those examples coming from individuals' behaviors. Now, what about if you want to do situational awareness from the city? You know, data might come in from different sources. How do we know there's a big event? There was an accident, or there was a lot of these things, right? So, these the applications are on basically behavior recognition on a larger scale. So one of the direction, also another direction we've been looking at is basically self-supervised learning on spatial temporal data, time series and spatial temporal data from the city. In here, we didn't use self-supervised learning. There's a paper right now currently under review that continued this work. But basically, the whole idea here, again, moving away from the aspect of feature engineering, trying to be able to align data and all that. Let's say if data coming in from different sources, it might be, you might have people checking in different location. You might have movement data from the sensors, the GPS traces, from the cars. How do we fuse them together right away in a deep learning pipeline? So what we think is the problem a lot of these is, how do we do both also long and short-term forecasting, not just short-term, but also long-term, so multiple steps ahead. We can use graph-based paradigm where each of these data is represented as a graph. It might be the road network and the relationship are represented as distance-based graph. And then in terms of the neighbor, it might be network distance, might be looks like it's close, but in terms of concepts or semantic, they're not neighbor. For example, semantic of a concept, say, let's say here, canteen maybe is related more with a school, but not with office, although they next to each other. You know what I mean? So how do we represent each of these, and how do we fuse them dynamically? So we borrow the aspect of cross attention from transformer. We use it for multiple graph as well. So that's basically what we did in this paper. We expand this further at the moment. I have got no slide about that in this work, but combining the self-supervised paradigm. For example, if data is missing, how do you then learn and then augment that data in order to improve the robustness of the model? Another work that we are going at the moment is continual learning. Continual learning is when behavior, so lifelong learning. So the model you are deploying is becoming outdated because behavior change. So in here, for example, the case study we use is a snowstorm, and also in the US, and also COVID lockdowns. And so the prediction that we want to do is how many people will be, so it's basically traffic prediction or demand prediction for train, buses, for taxis and bike share and e-scooter. So for example, these models are used normally for transport urban planning purpose, right? But when societal events happen, holiday, pandemic, or extreme weather events happen, it may not be able to pick up. There's an error here. For example, this is state of the art GWNet. That's a ground truth. As you can see, there's a snowstorm, and then it's gone. Like people, traffic and mobility is flat, whereas GWNet predict there's still it's not completely flat here, and that's basically our model. We initially there was a huge error. We found, oh, oops, something's wrong, and then we can correct them in the long term. And then as it picked up again, the recovery phase. We managed to pick them up as well. So that's basically what we did in this paper. It could detect the real world event, a societal event, and then it has and look at the changes over time as well. We tested on Blizzard Jonas datasets. That's in your state, isn't it? No? No, it's Washington State in DC. It's not Washington State, it's in DC. And also COVID, 3 waves of COVID. So take a look at details of the paper. About the key technique here is we have what we call memory. We have a memory in the network. So because the problem is catastrophic forgetting. So how do we embed a memory that there's something quite similar further down in few years? Maybe it sounds a bit like, you know, a holiday period when we have to readjust or things like that. Because normally when you have short-term forecasting like this, they only remember what's actually recent, not further down. So how do we actually relearn that? Okay, very quickly. How do we use language model for time series forecasting prediction? So the work we've been doing is then typically with time series forecasting, you've got a series, you might have encoder decoder, and you predict the next number, right? So numbers in, numbers out. Now, how do you leverage language models? Hang on, sorry. Housekeeping, knocking on my door. All right. If you want to use any large language model, let's say from Hugging Face API, it only takes text. So we actually change a whole paradigm of, you know, how do we change this sequential series as like a text? And we also prompt, so textual prompt, and the result is also a text out. So the benefit of this, of course, then, you know, it democratizes a model like, you know, whatever is already deployed to be used on a historical pattern or time series. And you just have to describe them and hopefully you get your answer correctly. And what we found also recently, right? So even ChatGPT can answer some math reasoning questions. So we were surprised ourselves when we had this paper. So this was published in February 2022. We started doing this from early 2021. We were surprised ourselves with the power of this. We got inspiration from CLIP, again, pre-trained transformer, multimodal can be used for you know, describing, for example, a text and then describe an image, and also DALL-E. And then we thought, okay, can we do the same for sensors? So what we did in this paper, we have these different descriptors, place of interest, observation, mobility data, and then we ask how many people will be here. So we basically transform our data sets to a mobility description using template. So in this example is mobility. You could do it for anything else. You can do it energy data. We've done it for energy data, for example. We've done it for movement data. And currently we're working on activity data for sensors. So if you look at this, we used SafeGraph data across 3 cities, NYC, Dallas, Miami, across 4 or 5 months. And we actually compared our model. So this was actually not using language model. This was still just using mobility descriptor, and we have also numerical encoder. So we have the two branches here, the natural language branch and mobility branch, and we basically simultaneously compute the two and then basically try to minimize the prediction loss. The state of the art we compare ourselves with, for example, Informer. This was actually the best paper award winner from AAAI 2021. So this was designed for time series forecasting, transformer based for time series forecasting. Our model actually outperformed in some cases Informer, in some cases they win. But remember, in here this model is very complex, where ours, we actually just have the very simple natural language branch and numerical branch. And these are some explanation, interpretability, why it works. We still can't explain it fully, so there's an ongoing work why. So the talk can actually pick up some interesting, when you visualize attention, there's some relationship between certain numerical patterns with, let's say, for example, coffee shop. And in this paper in 6 Spatial last year, we use directly things like GPT, so something pre-trained. This was GPT-2, for example. And we just introduced an auxiliary POI classifier, and we embed that as a token in a series. So for example, from whatever these are, the POI and the category target, which is pre-trained. I mean, which is a part of this POI classification auxiliary task. And we just use BERT, for example, or Roberta or XLNet. And again, compare ourselves with, let's say, Informer, or even the most recent one, AutoFormer. I think it's an ICML paper. Our work actually outperformed those, which is quite strange. I mean, we were ourselves surprised when we did this. And this is zero-shot setting. We train on NYC, we test on Miami and Dallas. It works. So let's say we don't see any Miami Dallas data, and you know, right? These cities are very different. NYC is very dense, right? And Dallas is a lot and very spread. But it actually worked. Well, there are a lot of other feature work, representation learning in task agnostic way. How do we make sure the representation transferable across different tasks? We haven't done them really. As you see, we tried to do it with updating the pre-training model with the 30 data sets from UCI time series. Some work and some don't. We still can't explain why. We're trying to work on this. And how do we get them to be robust in data that's irregular? And how do you make sure that it can handle data side bias? Anyway, I'm also part of UNSW Institute, and I'm one of the leaders. It's university-wide, so I'm sure there are a lot of people that you could potentially connect with, not just me. We work a lot with people from different fields. And I'm also co-leading this Center of Excellence that look at ethical and responsible automation making and AI. And one of the aspects that we look at, for example, the project I'm leading is called Transparent Machines. This look at explainability. And recently, we also won an NSF CSIRO grants on responsible creatable AI. So that those two colleagues of mine, the director on this, chief scientist Toby Walsh, director Harris Aziz, they're very much more in game theory and collective decision making. So they have this project awarded, and I've got this understanding bias in AI models for predictions of infectious disease spread. Again, the idea of using self-supervised learning so early when you don't have much data, and combination with agent-based modeling to model the future, for example. That's basically what we did. What we plan to do. No, we haven't done them. So we just got the award. Thank you so much. Any questions?
Thank you. Wow, there's a lot to benefit from this, and go and read all your papers to understand more of the details. So you can put your questions in chat, or better yet, raise your hand. I know Maureen did put a question in chat about the shift idea, and was hoping you could give a little more detail on that.
Oh, you mean, sorry, I haven't seen the question.
Actually, Diane, it was a question for you to help me later with that idea.
Oh,
I think it's something that she needs.
that's why she didn't see the question. Okay, absolutely.
I was going to let you guys ask the questions, but Flora, I just wanted to say that I really liked all of the work, and especially the lifelong learning. That was something I hadn't really seen before with these models, and I think that's really something that's going to be needed for sure.
Yes, yes. Fantastic. So I guess I'll start out with one question and open up to others before I have a second question. I like your new approach using contrastive learning for change point detection and time series segmentation. And, you know, when you look at contrastive learning, the pictures of animals are so distinct because they come from different species. When you look at time series data, sometimes you're trying to differentiate categories that are very obviously different, sleep versus wake. Other times they're much more subtle. And when you take a traditional statistical approach, you know, you have to kind of fine tune all the hyperparameters according to how subtle these changes are. And I'm wondering if your approach is robust to these different levels of subtlety in the changes between the underlying processes or activities.
No, that's a really, really good question, Diane. To be honest, our evaluation is still very limited in that paper in TSCP2. We did not do what the case where we combine all of these different representation in one pre-trained model, and then, you know, fine tune it for different cases. So that in that case, we only basically use that data set alone to do the pre-training. So that's basically an ongoing work. We currently doing them for because the current paradigm meter, you can have data sets coming from one domain, you build pre-training and you can transfer them. But if, let's say, you want to do them across all, right, different modality. So in terms of, for example, what we did, even for the COCO, that's also for multiple different, in COCO case, right? In COCO case, there are some data sets like opportunity, which I think you're very aware of that, right? That comes from different senses. The nice thing about self-supervised learning, and if you have your objective function designed correctly, and I think we did with COCO, it will be able to pick up the right signals and build a compact representation out of for the task you're interested in. Yeah, right. But we haven't done the evaluation where we combine all of those and build a massive super pre-trained model, like, you know, what ChatGPT does, like GPT does on all text, right? So, I mean, that's obviously something we could do as well.
Very interesting. Anybody else? I see there's another raised hand. Larry?
Yes, hi, this is Larry Holder. I guess my question is that the speech recognition models seem closer to, you know, time series prediction than a large language model. And I was wondering if, you know, you could do something similar with what you're doing with large language models, but using the ASR models, you know, perhaps even pre-trained ASR models just to do activity recognition. Is that even worth trying? Or
oh, that's a great comment. No, we haven't looked at speech recognition. So if you have any recommendation data set to look at, please, happy to look at them.
Okay, I'll try to find some. It's not my area, but I was just curious if it was worth trying. So. Thank you.
That's great. Thank you. Any other question?
There's a question that was posted in the Q&A, and that was, have you ever used frequency spectrograms of smartwatch sensor data for annotation as opposed to, you know, the raw signal data?
Yeah, so I think you can do whatever transformation that you need, right? Or for example, you could see the age-based SSL that we did. We did SSL for we did the contrastive between the raw data and the wavelet transformation. You can also do frequency based, but simply we use the wavelet based because it's a ECG kind of data set. Sorry, ECG or EEG, I can't remember. But basically, if you look at that, yeah, you can do different kind of transformation. In fact, that's basically the intuition behind self-supervised learning. You compare with the same, and you can say these are the positive pairs, whatever transformation that is, right? You can do multiple transformation if you want, but these are the same data sets and they belong to the same label.
Thank you. And I have one question, and it might be as simple, yes, it already does that answer, but I really enjoyed your discussion of the multiple modality learning. And we have an ongoing data set in which we have quite a few different modalities: smart home and smartwatch and EMA report and object use and audio data and clinical assessment data. And they are collected at different time points with some overlap. And we are also attempting to do some incremental model refinement, but again, sometimes some of the data are available and others are not. So would your approach to both the multiple modality learning and the incremental learning be able to accommodate such a case where they are time synchronized, but they're obviously at different sample rates, but also sometimes one modality is available and sometimes others?
Very, very good. There are the papers I have not covered in my talk, but let me just find it. There's ODE based techniques that I think really, really good for imputation. Let me just find those paper for you. It's called here. And there's another one. So in these two papers, if some modality are missing, how can even you use them? So the first paper was about data not fully aligned. Maybe some you might have an early sequence, and because you have started collecting this data, but you don't have other data sets yet. Can you start get the data coming in and, having them parallelized and then still learn them together? And the second case is that aspect where you have data with different representation and some are missing. So I think the second paper will also work really well.
Yes, that is exactly what I was asking. Terrific. Yeah. I will take a look.
Yeah. So this paper is still under review, so I haven't prepared the slides for this one. That's why I haven't discussed them.
Thank you for giving us this early insight. Any other questions? I think that we're all blown away and we're just going to go take time to learn more about everything that you're doing.
Ali Reza.
Ali,
can I ask a question?
Yeah, sure.
So my question is about the dispersal. Do you apply the dispersal on each individual dimension separately? So I see you have data set that's a half 10, 18 dimensions. So do you just
we put them together? Yeah, it works on multivariate. Yeah, that's the idea.
And it's not really a research question, but the usual figures, which is in your paper too, one of them was in EKG data, one of them was RFID data. The EKG data, I didn't see any references in the paper. Is it available for download? And the RFID paper, I checked it, but I couldn't find a link to the data set. Is it possible to?
Can you send me the specific question? So
yeah,
I'm sure I think they're all public data sets.
Okay, awesome. Thank you.
Okay. Thank you.
Yeah, thank you so much, Flora. I appreciate your time, and we all learned a lot. So enjoy the rest of your time in the US, and we'll talk soon.
Thank you. Bye.
Thank you. Bye.